Hello there, and welcome back to the Science Sleepy Minds, that cozy little corner of the internet where the universe whispers its secrets while you drift toward dreams. Tonight, you find yourself standing on an invisible platform suspended somewhere in the velvet blackness of space. Below your feet, there is nothing. Above your head, there is everything. Stars pepper the darkness like salt spilled across a black marble countertop, and somewhere out there, spinning lazily like a cosmic pinwheel, sits the galaxy you call home, the Milky Way. You have seen pictures of it, those gorgeous spiral renderings with sweeping arms of blue and pink, and you have probably felt a swell of pride thinking about how magnificently vast your galactic address must be. Well, friend, scientists have finally measured the thing properly, and it turns out our galaxy is a bit more modest than the brochure suggested. You probably will not survive the existential recalibration this information requires, but that is perfectly fine because you are lying somewhere comfortable, and by the time we finish, you will be too drowsy to care about cosmic humiliation. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment telling me where you are listening from, what time it is there. I always love knowing that someone in Tokyo at 3 in the morning and someone in Buenos Aires at sunset are both floating through the same story with me. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You take a breath, and the platform beneath you begins to drift. Not falling, just gliding, as though the universe itself has decided to give you a tour. The first thing you notice is that the stars are not evenly distributed. They cluster in places, thin out in others, forming a hazy band that stretches across your field of vision like a river of light frozen mid-flow. This is the Milky Way as seen from within, and for most of human history, people had absolutely no idea what they were looking at. To the ancient Egyptians, this glowing streak was the celestial Nile, a heavenly mirror of the river that gave them life. To the Greeks, it was the milk of Hera sprayed across the heavens when baby Heracles nursed a bit too enthusiastically. The name stuck, which is why you live in a galaxy named after a divine dairy accident. But names aside, nobody understood the scale of what they were seeing. How could they? Standing on a planet that seemed like the solid, unmoving center of everything, early humans looked up and saw lights. Some lights wandered, so they called those planets. From the Greek word for wanderer, other lights stayed fixed, so they called those stars. And that milky smear connecting them, divine mystery, best left to poets and priests. The idea that each of those tiny points of light might be a sun like your own, possibly with worlds orbiting them, possibly with creatures lying awake at night wondering about you, that concept would have sounded like madness. And yet here you are, drifting through the proof that madness was actually prophecy. Your platform rotates slowly, and you see the galaxy from a new angle. The spiral arms curl outward like the grooves of a vinyl record, except this record holds 400 billion stars instead of a single album. 400 billion. That number gets thrown around a lot, but let it sink in for a moment. If you counted 1 star per second without sleeping, eating, or taking bathroom breaks, it would take you roughly 12,000 years to finish. Historians still argue whether the Great Pyramid of Giza took 20 years or 40 years to build, and either way, that is a blink compared to the time needed just to count our local stars. You're not going to count them tonight. You're going to do something far more reasonable, which is relax while scientists explain why even that staggering number lives inside a structure smaller than we once believed. For decades, textbooks confidently stated that the Milky Way measured between 100,000 and 180,000 light years across. That is a comfortably enormous number. A light year, after all, is the distance light travels in a single year, roughly 6 trillion miles. Multiply that by 100,000, and you have a disk so wide that even light itself, the fastest thing in existence, needs 100 millennia to cross it. You could leave Earth on a beam of light right now, and your great multiplied by thousands grandchildren would still be waiting for you to reach the other side. That kind of scale should make you feel cosmically significant, a citizen of a grand galactic empire. Except recent measurements tell a slightly different story. Using data from the Gaia space telescope and refined observations of the stars at the galaxy's edge, astronomers have concluded that the Milky Way's stellar disk is closer to 100,000 light-years, perhaps even a touch under. Not 180,000, not the generous upper estimates that made us feel like the big kids on the cosmic block. Our galaxy, it turns out, is respectably sized but not exceptional. It is the galactic equivalent of a mid-size sedan, practical, reliable, nothing to be ashamed of, but certainly not the luxury cruiser we imagined. And that, dear traveller, is where tonight's journey truly begins. You're going to trace the history of how humans figured out the size of their galaxy, stumbling through millennia of wrong guesses, brilliant accidents, and telescopes that revealed more than anyone was emotionally prepared to handle. Your platform drifts backward through time now, the stars smearing into streaks before resolving again into a different sky. You find yourself hovering above ancient Mesopotamia, the land between the rivers, where some of humanity's earliest astronomers squinted at the heavens and tried to make sense of the chaos. Below you, ziggurats rise from mud brick cities, their stepped pyramids serving as both temples and observation decks. Priests climb to the top each night, clay tablets in hand, recording the positions of stars and planets with a dedication that would make modern graduate students weep. The Babylonians were remarkably good at this. By around 1200 BCE, they had catalogued hundreds of stars, tracked the movements of visible planets, and developed mathematical models that could predict lunar eclipses with unsettling accuracy. They divided the sky into 12 sections, creating the zodiac that astrologers still reference today, though the Babylonians were less interested in personality assessments than in figuring out when the gods might smite someone. Their star charts were practical tools, used for agriculture, religious ceremonies, and royal decision-making. If Mars appeared too close to a certain constellation, perhaps the king should delay that military campaign. If Venus rose at an odd angle, maybe the harvest would fail. What the Babylonians did not do, however, was worry much about distance. The stars were lights fixed to a celestial sphere that rotated around the Earth, and that was sufficient explanation. How far away were they? Far enough. The concept of measuring interstellar distance in any meaningful unit simply did not exist. The universe was a dome, Earth was the floor, and everything else was decoration arranged for human benefit. It sounds arrogant now, but remember, these were people who had never seen a photograph of Earth from space. They had no reason to suspect they were living on a spinning rock, hurtling through an infinite void. The evidence available to them suggested a cozy enclosed cosmos, and they built their models accordingly. You drift westward, your platform carrying you over the wine-dark Aegean Sea to ancient Greece, where philosophers are about to make things simultaneously better and worse. The Greeks inherited Babylonian astronomical data and decided to argue about it, which is essentially the Greek contribution to every field. Thales of Miletus proposed that the Earth floated on water, which at least replaced divine turtles with something observable. Anaximander suggested the Earth was a cylinder suspended in space, with humans living on the flat top. Pythagoras, famous for triangles, argued for a spherical Earth, which turned out to be correct, though his reasoning involved mystical beliefs about spheres being the most perfect shape rather than actual evidence. But it was Aristotle who codified the geocentric model that would dominate Western thought for nearly 2,000 years. Earth sits motionless at the centre of the universe, The moon, sun, planets and stars all orbit around it in perfect crystalline spheres. The stars occupy the outermost sphere, fixed in place like jewels embedded in glass. Beyond the stars lies the realm of the divine, the unmoved mover, the prime cause of all celestial rotation. This model was elegant, philosophically satisfying, and spectacularly wrong, but it matched everyday observation so well that questioning it seemed absurd. You do not feel the Earth moving, do you? When you jump, you land in the same spot, not miles away because the planet rotated beneath you. Aristotle's cosmos made sense, and sense is a powerful drug. One quirky exception to Greek geocentrism came from Aristarchus of Samos, who proposed around 270 BCE that the Earth actually orbited the Sun. He even attempted to calculate the relative distances of the Sun and Moon using geometry during lunar eclipses. His methods were sound, but his measurements were off, leading him to conclude the Sun was about 20 times farther than the Moon. The real number is closer to 400 times, but still, the man was trying. Unfortunately, heliocentrism was too radical for his contemporaries. If the Earth moved, surely we would feel it. If the Earth moved, surely the stars would shift position as we orbited, a phenomenon called parallax. Since nobody could detect stellar parallax, the Earth must be stationary. Aristarchus was ignored. His ideas shelved for 18 centuries until a Polish astronomer named Copernicus dusted them off. The Greeks also attempted to measure the size of the Earth itself, which is at least a prerequisite for understanding your place in anything larger. Eratosthenes, working in Alexandria around 240 BCE, noticed that at noon on the summer solstice, the sun shone directly down a well in the city of Syene, casting no shadow. Meanwhile, in Alexandria, a vertical stick cast a measurable shadow. Using geometry and the known distance between the two cities, Eratosthenes calculated the Earth's circumference with remarkable accuracy, landing within a few % of the modern value. This was genuine science, observation leading to measurement leading to knowledge. But even Eratosthenes had no way to extend his methods to the stars. The celestial sphere remained a mystery, its distance effectively infinite, its nature divine. Historians still argue whether the Greeks genuinely believed in physical crystalline spheres or used them as mathematical conveniences, abstract models to predict planetary positions without claiming literal truth. Either way, the result was the same, a universe fundamentally centered on human existence, with stars serving as a glittering boundary rather than destinations. You could not travel to them any more than you could travel to heaven. They were simply there, beautiful and unreachable, forever fixed in their patterns. Your platform rises now, leaving the Mediterranean behind, ascending through centuries of scholarship that preserved Greek ideas, translated them into Arabic, and eventually fed them back into medieval Europe. The geocentric model survived barbarian invasions, the fall of Rome, and the rise of Christianity, which found it theologically convenient. Earth at the centre meant humanity at the centre, which meant God's special creation occupied a privileged position. Challenging that arrangement was not just scientifically bold, it was spiritually dangerous. And so the Milky Way remained unexplained milk. The stars remained fixed lights, and nobody seriously asked how big the galaxy was because the concept of a galaxy did not yet exist. You descend now through the amber haze of a Renaissance evening, your platform settling near a modest house in Padua, where a middle-aged professor is about to ruin everyone's comfortable assumptions. The year is 1609, and Galileo Galilei has just received word of a curious Dutch invention, a tube with lenses that makes distant objects appear closer. Within months, he has built his own version, improved it significantly and pointed it at the night sky. What he sees will crack the celestial sphere like an egg. The moon, that perfect heavenly body, turns out to be covered in mountains and craters, as rugged and imperfect as Earth itself. Jupiter, observed over several nights, reveals 4 tiny points of light that orbit around it, proving that not everything in the universe revolves around our planet. Venus shows phases like the Moon, waxing and waning in ways that only make sense if it orbits the Sun. And the Milky Way, that divine streak of celestial milk, resolves into countless individual stars, so numerous and faint that the naked eye blurs them into a continuous glow. You watch Galileo pull his eye from the telescope and sit back, stunned. He's not a young man prone to flights of fancy. He's a professor of mathematics, cautious by nature, deeply aware that publishing these observations will invite trouble. But he publishes anyway, releasing a small book called Sidereus Nuncius, the Starry Messenger, in 1610. The response is immediate and polarized. Some scholars celebrate, others refuse to even look through the telescope, insisting that the lenses must be producing illusions. Why would God create a universe with moons orbiting other planets? What possible purpose could that serve? The theological implications are genuinely troubling for the era. If the stars are not fixed to a single sphere but scattered through space at varying distances, then the cosmos has no clear boundary. If the Milky Way is made of stars, then there are far more stars than anyone imagined, possibly infinite. And if the Earth orbits the Sun, then humanity is not stationed at the centre of creation, but perched on a moving rock circling a fire like a moth around a candle. This is not merely a scientific adjustment, it is a complete philosophical eviction notice. Galileo's support for heliocentrism eventually earned him a trial by the Inquisition, house arrest, and a forced recantation. Historians still argue whether he muttered, "and yet it moves," under his breath after renouncing the Earth's motion, a defiant whisper that probably never happened but feels true enough to persist as legend. What definitely happened was that his observations could not be unseen. Other astronomers built better telescopes, confirmed his findings, and expanded on them. The crystalline spheres shattered, and the universe became a place where stars were suns, possibly with planets, possibly with life, stretching into distances no human had ever contemplated. But here is the irony that makes astronomers chuckle at cocktail parties. Even after Galileo proved the Milky Way was made of stars, nobody had any idea how far away those stars were or how large the resulting structure might be. The Milky Way went from divine mystery to stellar collection, but its dimensions remained unknown. You could count the stars if you had infinite patience, but you could not measure the space between them. Distance. That stubborn property still refused to cooperate. Your platform drifts forward a few decades to the observatory of Johannes Hevelius in Gdansk, where a wealthy brewer with a passion for the sky is building the longest telescopes in Europe. His instruments are absurd, some stretching over 100 feet, requiring elaborate scaffolding and teams of assistants to operate. The length reduces optical distortions, allowing clearer images, and Hevelius uses them to map the moon in unprecedented detail, naming craters and mountains that bear his designations to this day. But even his magnificent tubes cannot reveal stellar distances. The stars remain points of light, stubbornly refusing to show the disks that would indicate their true sizes and distances. Part of the problem is conceptual. If stars are suns, they must be incredibly far away to appear so faint. But how far is incredibly far? Without a reference point, without a cosmic ruler, distance estimates devolve into poetic guesses. Some astronomers suggested the nearest stars might be a few hundred times farther than the Sun. Others proposed thousands. The actual answer, that the nearest star system beyond the Sun lies over 4 light-years away, roughly 25 trillion miles, was so extreme that proposing it would have seemed like exaggeration for its own sake. Another part of the problem is technical. To measure stellar distance, you need to detect parallax, the apparent shift in a star's position as Earth orbits the Sun. Imagine holding your thumb at arm's length and closing one eye then the other. Your thumb seems to jump against the background. The same principle applies to stars, except the baseline is Earth's orbit, about 186 million miles across, and the stars are so distant that their parallax shifts are tinier than the errors in most instruments. For centuries, astronomers searched for stellar parallax and found nothing, which either meant the Earth was not moving or the stars were absurdly far away. The second option was correct, but proving it required technology that would not exist for another 200 years. Meanwhile, the Milky Way remained a mystery in plain sight. You could see it on any clear night, that luminous river arching overhead, but you could not determine whether it was a flat disk, a sphere, a ribbon, or some shape no one had imagined. Galileo showed it was made of stars. Subsequent observers confirmed that those stars were not uniformly distributed. Darker patches interrupted the glow, lanes of shadow that we now know are dust clouds blocking the light behind them. But without distances, without a three-dimensional map, the Milky Way was a photograph without depth, a puzzle without edges. You rise again, leaving the age of early telescopes behind, floating toward the 18th century where a musician turned astronomer is about to attempt the first systematic survey of the galaxy. He will get many things wrong, but he will also invent the method that makes progress possible, counting stars direction by direction and assuming their apparent density reveals the shape of the whole. The night air over Bath, England carries the faint scent of coal smoke and ambition as your platform settles near a modest house in 1781. Inside, a German-born musician named William Herschel is hunched over a homemade telescope, grinding his own mirrors with a perfectionism that borders on obsession. He has already discovered a new planet, the one we now call Uranus, and the shock of that find has transformed him from amateur stargazer to professional astronomer overnight. King George III, delighted that the heavens have yielded fresh territory, grants Herschel a royal pension, freeing him from teaching music lessons and allowing him to focus entirely on the sky. Herschel decides to do something no one has seriously attempted. He will count the stars. Not all of them, obviously, because even then people understood there were too many, but a representative sample in every direction. By comparing how many stars appear in different parts of the sky, he hopes to infer the shape of the structure containing them. If stars cluster densely in one direction, that direction must extend farther. If they thin out quickly in another direction, that boundary must be nearby. It is a reasonable method, and it requires only patience, a good telescope, and a willingness to spend countless nights staring at tiny points of light until your eyes water. Working alongside his sister Caroline, who becomes a renowned astronomer in her own right, Herschel conducts what he calls star gauges. He points his telescope at a specific region, counts every star visible in the field of view, records the number, then moves to an adjacent region and repeats. Over years, he builds a dataset spanning the entire sky visible from England, a monumental effort that would make modern astronomers weep with sympathy. There were no cameras, no computers, no graduate students to delegate to, just two people, a telescope, and a notebook. The results, published in 1785, reveal a flattened structure. Stars cluster most densely in the band of the Milky Way and thin out rapidly perpendicular to it. Herschel concludes that the galaxy is shaped like a grindstone or a lens, thick in the middle and tapering at the edges. More controversially, he places the Sun very close to the centre of this structure, reasoning that since stars appear roughly equally dense in all directions along the Milky Way's band, we must be near the middle. If we were off to one side, the star counts would be lopsided, denser toward the galactic centre and sparser toward the edge. This is elegant reasoning undermined by a flaw Herschel could not have anticipated. interstellar dust. The dark patches scattered throughout the Milky Way are not empty regions, but clouds of microscopic particles that absorb and scatter light. These clouds create the illusion of fewer stars behind them, fooling any observer who assumes stars are evenly distributed. Herschel's star gauges were actually measuring where dust blocked his view, not where the galaxy ended. The sun appeared central because dust dims stars equally in every direction, masking the true structure. But Herschel did not know about interstellar dust. Nobody did. The concept would not be confirmed until the 20th century, when astronomers noticed that distant stars appeared redder than expected, their blue light absorbed by intervening particles. In Herschel's time, the space between stars was assumed to be perfectly transparent, a void through which light travelled without interference. Given that assumption, his conclusions were logical. They were also wrong, but being wrong for understandable reasons is how science works. Historians still argue whether Herschel truly believed the sun was central, or whether he acknowledged the limitation of his methods. His writings suggest awareness that his model was provisional, a first approximation subject to revision. He knew he could not see through the galaxy's equator, that dense star fields defeated his counting method, that the true extent might far exceed his measurements. But provisional models have a way of hardening into dogma when repeated often enough, and for over a century the idea of a sun-centered galaxy persisted in textbooks. Herschel estimated the galaxy's size at roughly 800 times the distance to the bright star Sirius, which he guessed lay about 2 light-years away. His Sirius estimate was off by a factor of 4. The actual distance is roughly 8.5 light-years, but even with that error, his galaxy model implied a structure thousands of light-years across, containing hundreds of millions of stars. This was already unimaginably vast by human standards, yet it was still a colossal underestimate. The true Milky Way is about 100 times larger and contains perhaps 1,000 times more stars. One quirky contribution from this era came from Thomas Wright of Durham, who in 1750 proposed that the Milky Way might be a thin shell of stars surrounding a divine centre, with the sun embedded somewhere within the shell. Viewed from inside, such a shell would appear as a band across the sky, exactly as observed. Wright was wrong about the shell, but right about the band being a perspective effect, and his ideas influenced later thinkers even if his mystical motivations seem strange today. Your platform rises as dawn breaks over Bath, the stars fading into a brightening sky. Herschel will continue observing for decades, cataloguing nebulae, double stars and moons of distant planets. His son John will extend the star gauges to the southern hemisphere, mapping regions invisible from England. Together they build the foundation for future galactic astronomy, even if their central conclusions need drastic revision. The grindstone model of the galaxy, with the sun near its centre, remained scientific consensus well into the 19th century. Challenging it requires new tools: photography to record faint stars beyond the limit of the human eye, spectroscopy to analyse starlight for clues about distance and motion, and eventually a cosmic yardstick that can reach beyond the veil of dust. That yardstick is coming, but it will emerge from an unexpected place. A quiet observatory in Massachusetts, where a woman paid to do clerical work will notice a pattern that changes everything. The year is 1908, and your platform drifts through the crisp autumn air of Cambridge, Massachusetts, settling near a brick building with a domed roof. This is the Harvard College Observatory, and inside a small army of women is doing work that most male astronomers consider beneath them. They're called computers, a job title that predates the electronic kind, and their task is to examine glass photographic plates of the night sky, cataloguing the brightness and positions of thousands of stars. The pay is minimal, the hours are long, and the work is repetitive. But among these women, one will make a discovery that unlocks the distance to the stars. Her name is Henrietta Leavitt, and she's studying a peculiar type of star found in the Small Magellanic Cloud, a fuzzy patch of light visible from the southern hemisphere. These stars pulse, brightening and dimming in regular cycles that range from a few days to several weeks. They are called Cepheid variables, named after the star Delta Cephei, the first of their kind identified. Astronomers have known about Cepheids for over a century, but nobody has figured out why they pulsate or whether their pulsations mean anything useful. Leavitt begins photographing the Small Magellanic Cloud repeatedly, tracking individual Cepheids through their cycles. She notices something remarkable. The brighter a Cepheid appears on average, the longer its pulsation period. A star that takes 30 days to complete a cycle is intrinsically brighter than one that takes 3 days. This is not merely a correlation, it is a tight, predictable relationship, a law of nature hiding in plain sight. Why does this matter? Because all the Cepheids in the Small Magellanic Cloud are roughly the same distance from Earth. The cloud is a distinct structure, a satellite galaxy orbiting the Milky Way, so any brightness differences among its stars reflect actual luminosity differences, not distance effects. Leavitt's period luminosity relation means that if you know a Cepheid's period, you know its true brightness. And if you know its true brightness, you can compare it to its apparent brightness and calculate how far away it is. Imagine a row of identical flashlights stretching into the fog. The closer ones appear brighter, the farther ones appear dimmer. If you know the wattage of each flashlight, you can calculate its distance based on how bright it looks. Cepheids are cosmic flashlights with their wattage stamped on the label in the form of pulsation period. Leavitt has handed astronomers a ruler that works across interstellar distances. She publishes her findings in 1912, modestly titled Periods of 25 Variable Stars in the Small Magellanic Cloud. The paper is short, the conclusions understated, and Leavitt receives little immediate recognition. She continues working at Harvard, cataloguing stars, her health deteriorating from undiagnosed stomach cancer. She dies in 1921 at the age of 53, never fully aware of how profoundly her discovery will reshape astronomy. Historians still argue whether she should have received a Nobel Prize, noting that the award requires the recipient to be alive and that her early death precluded consideration. Others recognize the implications faster than the world recognizes Leavitt. Einar Hertzsprung, a Danish astronomer, attempts to calibrate her relation by measuring distances to nearby Cepheids using parallax. He gets the calibration wrong by a factor of several, a mistake that will propagate through astronomy for decades, but the method itself proves sound. Harlow Shapley, a young American astronomer working at Mount Wilson Observatory in California, takes Leavitt's discovery and aims it at the Milky Way. Your platform glides westward, crossing the continent to a mountaintop observatory that houses the largest telescope in the world at this time, the 60-inch reflector on Mount Wilson. Shapley is using it to study globular clusters, those dense spherical swarms of ancient stars that orbit the galaxy like bees around a hive. Globular clusters contain Cepheids, and Cepheids can reveal distances. Shapley realizes that if he can map the positions of globular clusters in 3 dimensions, he can determine the shape and size of the galaxy itself. What he finds is startling. The globular clusters are not evenly distributed around the Sun. They cluster preferentially in one direction, toward the constellation Sagittarius. This asymmetry suggests that the Sun is not at the center of the galaxy, but off to one side, orbiting like any other star. The globular clusters, by contrast, swarm around the true galactic center, a point hidden behind the dense star fields and dust clouds of the Milky Way's inner regions. Shapley announces his conclusions in 1918. The Milky Way is far larger than anyone thought. perhaps 300,000 light-years across, and the Sun lies roughly 50,000 light-years from the centre. These numbers are too large, inflated by calibration errors in the Cepheid relation and by the still unrecognised effects of interstellar dust. But the fundamental insight is correct. Humanity is not centrally located. We orbit in the galactic suburbs, unremarkable in position as well as importance. This is the second great demotion in cosmic history. First, Copernicus moved Earth from the centre of the solar system. Now Shapley moves the Sun from the centre of the galaxy. The pattern is becoming clear. Every time humans assume they occupy a special position, the universe corrects them. Leavitt's yardstick will continue to be refined over the following century, its calibration tightened by parallax measurements from spacecraft like Hipparcos and Gaia. The period luminosity relation she discovered remains fundamental, used to measure distances not just within the Milky Way but to galaxies millions of light-years away. And speaking of other galaxies, a fierce debate is brewing about whether such things even exist. Your platform hovers now above a circular chamber filled with the murmur of formal debate and the rustle of scientific papers. The date is April 26, 1920, and you are witnessing what astronomers will later call the Great Debate, a public confrontation between two visions of the universe. On one side stands Harlow Shapley, fresh from his globular cluster work, defending a galaxy so enormous that nothing else could possibly exist outside it. On the other stands Heber Curtis, a seasoned observer from Lick Observatory, arguing that the spiral nebulae scattered across the sky are separate island universes, galaxies in their own right, far beyond the Milky Way. The stakes are staggering. If Shapley is correct, the Milky Way is everything. The cosmos contains one giant galaxy, a few 100,000 light-years across, and the spiral nebulae are merely gas clouds within it. If Curtis is correct, the Milky Way is one galaxy among many, possibly billions, and the universe is incomprehensibly larger than anyone has imagined. The difference is not subtle. It is the difference between living in a single city and living on a planet covered with cities you never knew existed. Shapley presents first, defending his enormous galaxy. His evidence centres on the globular clusters and the Cepheid distances he has measured. The galaxy must be vast to accommodate them. The spiral nebulae, he argues, cannot be external galaxies because if they were, they would be impossibly distant. And one of them, the Andromeda Nebula, shows a rotational motion that implies it is spinning fast enough to fly apart if it were truly millions of light-years away. This argument is based on measurements by Adrian van Maanen, a respected astronomer who claims to have detected the rotation of spiral nebulae by comparing photographs taken years apart. Van Maanen's measurements are wrong, but nobody knows that yet. Curtis counters with observations of his own. He has studied novae, exploding stars that flare briefly before fading. Novae in the Andromeda Nebula appear far dimmer than novae in the Milky Way, suggesting that Andromeda lies at a much greater distance. He also points out that the spiral nebulae show dark lanes, reminiscent of the dust clouds in our own galaxy, implying similar structure, and he disputes Shapley's galaxy size, arguing that calibration errors have inflated the distances. Historians still argue whether the Great Debate produced a clear winner on the day. Contemporary accounts suggest the audience left uncertain, with both speakers making compelling points. The resolution would come not from rhetoric but from observation, and it would require a telescope larger than any then in existence. That telescope is already under construction, the 100-inch Hooker telescope on Mount Wilson, destined to be the largest in the world for nearly 3 decades. Its mirror, cast from French wine bottle glass because no other supplier could produce a suitable blank, will capture light from objects fainter than any human eye could perceive. and the man who will use it to settle the debate is a Missouri-born lawyer turned astronomer named Edwin Hubble. Your platform drifts forward 4 years to a cold October night in 1923. Hubble is photographing the Andromeda Nebula, hoping to find novae that will help determine its distance. On the photographic plate, he spots what he initially marks as a nova, scribbling N beside it. But on subsequent nights, the star does not fade as novae do. It brightens and dims in a regular cycle. Hubble crosses out the N and writes var, variable. He has found a Cepheid. Using Henrietta Leavitt's period luminosity relation, Hubble calculates the distance to Andromeda, approximately 900,000 light-years. This is far beyond the boundaries of even Shapley's bloated galaxy. Andromeda cannot be a gas cloud within the Milky Way. It must be a separate galaxy, an island universe in its own right. The news breaks slowly. Hubble is cautious, verifying his results, finding more Cepheids, refining his calculations. By 1924, the evidence is overwhelming. He presents his findings to the American Astronomical Society on New Year's Day, 1925, and the astronomical community reels. The Milky Way, that magnificent structure Shapley defended so passionately, turns out to be merely one galaxy among countless others. Shapley, to his credit, accepts the new evidence gracefully. He had been wrong about the spiral nebulae, but right about the Sun's position within our galaxy. His career continues productively. He goes on to direct Harvard College Observatory and mentor a new generation of astronomers. Curtis savors vindication but focuses on other work. Van Maenen's rotation measurements are eventually exposed as errors, possibly caused by systematic biases in his photographic comparisons. The great debate ends not with a knockout, but with the slow accumulation of undeniable data. For the Milky Way, the implications are humbling. Once imagined as the entire universe, it is now revealed as a single galaxy in a cosmos filled with galaxies. Hubble's later work will show that these galaxies are receding from us. Their light stretch toward the red end of the spectrum, suggesting the universe itself is expanding. The Milky Way is not only one among billions, but also adrift in an expanding sea of space, carried along by forces that dwarf any human comprehension. Your platform rises as dawn breaks over Mount Wilson, the great dome closing against the morning light. The age of extragalactic astronomy has begun, and with it, a new urgency to understand exactly how large our own galaxy really is. Static crackles through the air as your platform descends into a post-war laboratory, cluttered with radio equipment and oscilloscope screens. The year is 1951, and the landscape of astronomy is shifting beneath your feet. Optical telescopes, for all their elegance, can only see what visible light reveals, and visible light is easily blocked by dust. The inner regions of the Milky Way, cloaked behind thick clouds of interstellar debris, have remained hidden for centuries. But radio waves pass through dust like whispers through curtains, and astronomers are about to hear the galaxy speak. The breakthrough begins with a prediction. In 1944, a Dutch astronomer named Hendrik van der Hulst calculates that hydrogen atoms in space should emit radio waves at a very specific wavelength, 21 centimeters, corresponding to a frequency of 1,420 megahertz. Hydrogen is the most abundant element in the universe, scattered throughout the galaxy in vast clouds. If astronomers can detect this emission, they can map the hydrogen and thereby trace the Milky Way structure in regions optical telescopes cannot reach. It takes 7 years to confirm the prediction. In 1951, Harold Ewan and Edward Purcell at Harvard detect the 21 centimeter line using a horn antenna mounted outside a laboratory window. Within weeks, Dutch and Australian teams confirm the detection independently. The race is on to map the galaxy in radio light. What emerges from these observations is spectacular. The Milky Way is not a featureless disk but a spiral galaxy, with arms of hydrogen and stars curling outward from a central bulge. Radio astronomers trace these arms by measuring the Doppler shift of the hydrogen emission, which reveals how fast the gas is moving toward or away from us. Combined with models of galactic rotation, these velocities translate into distances, allowing a three-dimensional map to emerge from the static. The spiral arms receive names borrowed from the constellations they pass through: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm. Our Sun sits on a minor spur called the Orion arm, sometimes poetically named the Orion Cygnus arm, a modest branch between larger structures. This placement reinforces the lesson Shapley taught. We're not in the galactic centre, not even on a major arm, but tucked away in an unremarkable suburban nook. Radio observations also reveal the galaxy's rotation. Unlike a solid wheel, the Milky Way rotates differentially. Stars near the centre orbit faster than those farther out, completing a circuit in less time. Our Sun, roughly 26,000 light-years from the galactic centre, takes about 230 million years to complete one orbit, a period sometimes called a cosmic year or galactic year. Dinosaurs last roamed Earth about half a galactic year ago. The previous orbit was completed before complex multicellular life existed. Historians still argue about priority in radio astronomy, with multiple nations claiming credit for key discoveries. The post-war era saw rapid military to civilian technology transfer, and teams in the United States, the Netherlands, Australia, and the United Kingdom often publish similar findings within weeks of each other. Collaboration and competition blurred together, driven by Cold War funding and the sheer excitement of a new observational frontier. One quirky footnote from this period involves the search for extraterrestrial intelligence. The 21-centimetre hydrogen line became a favoured frequency for SETI researchers, reasoning that any intelligent civilization would recognise its cosmic significance and might use it for interstellar communication. The logic was poetic. Hydrogen, the most common element, emitting at a wavelength that penetrates dust, seemed like a natural meeting point for beings trying to signal across the void. No confirmed signals have been detected, but the search continues, funded by enthusiasts and occasionally mocked by skeptics. Radio astronomy also revealed the galactic centre for the first time. Optical telescopes see only a dense wall of stars in Sagittarius, the accumulated glow of billions of suns piled behind one another and shrouded in dust. Radio waves penetrate this veil, exposing a complex region of hot gas, magnetic fields, and, at the very centre, an intense radio source called Sagittarius A star. This source, no larger than our solar system, anchors the entire galaxy with its gravitational pull. Later observations will confirm what radio astronomers suspected. Sagittarius A star is a supermassive black hole, containing roughly 4 million times the mass of the Sun. Your platform rises above the radio dishes scattered across continents, their parabolic faces aimed at the sky like ears listening for cosmic whispers. The Milky Way now has a shape, a barred spiral with a central bar of stars and gas feeding two major arms that wind outward like the springs of a watch. The size estimates remain uncertain, but the structure is undeniable. What radio astronomy cannot easily provide is mass. Hydrogen emission maps tell you where the gas is, but not how much dark matter lurks in the invisible spaces between. That mystery requires another approach, one that will reveal the Milky Way is far heavier than its visible stars suggest, and that most of its mass hides in forms no telescope can see. You settle into a lecture hall somewhere in the 1970s, the chalkboard covered in equations and the professor pacing with barely contained excitement. The topic is rotation curves, and the implications are about to overturn everything astronomers thought they knew about galactic mass. Here is the puzzle. When you measure how fast stars and gas orbit the centre of a galaxy, you expect the speed to drop off with distance. This is what happens in the solar system. Mercury races around the Sun at nearly 50 kilometers per second, while Neptune plods along at a leisurely 5. The reason is gravity. The farther you are from a central mass, the weaker its pull, and the slower you need to move to stay in orbit. Kepler worked this out 4 centuries ago, and it applies to any system dominated by a central mass. Except galaxies do not behave this way. When astronomer Vera Rubin measures the rotation curves of spiral galaxies in the 1970s, she finds that orbital speeds stay roughly constant far from the galactic centre. Stars at the edge of a galaxy move just as fast as stars halfway in. This should not happen. According to the visible mass distribution, those outer stars should be moving much slower, or they would fly off into intergalactic space like mud from a spinning tyre. The conclusion is inescapable. Galaxies contain far more mass than we can see. Something invisible is providing extra gravitational pull, holding those fast-moving outer stars in their orbits. This invisible something gets a name that sticks: dark matter. Dark matter is not merely unlit stars or black holes or gas too cold to emit detectable radiation. Careful accounting of all these ordinary forms of matter, collectively called baryonic matter, still falls short. Dark matter must be something else entirely, a new category of substance that interacts gravitationally but not electromagnetically. It does not emit, absorb, or reflect light. It is invisible in every telescope ever built, yet it outweighs the visible universe roughly 5 to 1. For the Milky Way specifically, dark matter changes everything about how we measure size. If you define a galaxy by its visible stars and gas, our galaxy extends perhaps 100,000 light-years across. But if you include the dark matter halo, that invisible sphere of gravitational influence surrounding the stellar disk, the Milky Way becomes enormously larger. The halo may extend 300,000 light-years or more, containing the vast majority of the galaxy's total mass, while remaining utterly undetectable by any direct observation. Historians still argue about who should receive primary credit for the dark matter concept. Fritz Zwicky proposed invisible mass in galaxy clusters as early as the 1930s, based on the surprisingly fast motions of galaxies within the Coma cluster. His estimates were rough, his personality abrasive, and his contemporaries largely ignored him. Vera Rubin's rotation curve work in the 1970s provided the definitive evidence that convinced the mainstream, but she never received the Nobel Prize many believed she deserved before her death in 2016. One quirky aspect of dark matter research is the proliferation of candidate particles that might compose it. WIMPs, weakly interacting massive particles, were long the favoured hypothesis, expected to produce detectable signals in underground experiments shielded from cosmic rays. Decades of searching have found nothing. Axions, another hypothetical particle, remain undetected as well. Some physicists have proposed modifying gravity itself to explain rotation curves without invoking invisible matter. But these modified gravity theories struggle to account for other observations, such as the behaviour of colliding galaxy clusters. For tonight's purposes, what matters is that the Milky Way's mass is dominated by something we cannot see. The stars, the gas, the dust, the planets, all the visible contents of the galaxy add up to a small fraction of the total. When astronomers talk about galactic size, they must specify what they mean: the stellar disk, the gas disk, or the dark matter halo. Each definition gives a different answer, and the largest component, the halo, is entirely invisible. Your platform rises, leaving the lecture hall behind. The Milky Way you thought you knew, 100,000 light-years of glowing stars, turns out to be the luminous tip of a much larger iceberg. The galaxy you inhabit is mostly dark, mostly mysterious, and far heavier than its light suggests. This revelation makes measuring the galaxy's size more complicated than simply counting stars. To truly understand the Milky Way's extent, astronomers need a cosmic census unlike any before, one that tracks not just brightness, but position, velocity, and distance for billions of individual objects. That census is coming, and it will arrive aboard a spacecraft named after a goddess of the Earth. Your platform ascends through the atmosphere, leaving Earth's surface behind, until you hover alongside a spacecraft drifting at the second Lagrange point, a gravitational sweet spot 1,000,000 miles from home. This is Gaia, the European Space Agency's mission to map the Milky Way with unprecedented precision. Launched in December 2013, Gaia spends its years slowly rotating, scanning the sky, measuring the positions and motions of nearly 2 billion stars. The core technique Gaia employs is parallax, the same method astronomers have attempted since Aristarchus noticed the moon shifted against the stars during a lunar eclipse. As Earth orbits the Sun, nearby stars appear to wobble slightly against the backdrop of more distant ones. The size of this wobble reveals the distance. Larger wobble means closer star. The challenge has always been precision. Stellar parallaxes are tiny, measured in milliarc seconds, angles smaller than the width of a human hair seen from miles away. Previous parallax missions, notably Hipparcos in the 1990s, measured distances to about 100,000 stars within a few hundred light-years of the Sun. Useful, but limited. Gaia aims for 1 billion stars, reaching tens of thousands of light-years into the galactic disk. To achieve this, the spacecraft carries 2 telescopes feeding a single detector array, measuring stellar positions repeatedly over its mission lifetime. Each measurement is imprecise on its own, but averaging billions of measurements over years yields accuracies that would have seemed magical to earlier generations. The first major data release came in 2016, the second in 2018, and subsequent releases have continued to refine the catalogue. Each release sends ripples through the astronomical community as researchers discover the galaxy is not quite what they expected. One surprising result involves the Milky Way's spiral arms. Ground-based observations suggested our galaxy had 4 major arms, but Gaia data reveals a more complex picture. The arms are not smooth, continuous structures, but fragmented, with stars of different ages tracing slightly different patterns. Young stars outline the classic spiral shape. Older stars spread more diffusely, their orbits perturbed over billions of years by gravitational encounters. The galaxy you imagined as a neat pinwheel is actually a messy dynamic system, constantly reshuffled by its own gravity. Another surprise involves the galaxy's history. By measuring the motions of stars in 3 dimensions, not just their positions on the sky, but their velocities toward and away from us, astronomers can rewind the clock and reconstruct past events. Gaia data reveals evidence of ancient collisions, smaller galaxies that crashed into the Milky Way and were absorbed, their stars now mingled with our native population, but still identifiable by their distinct trajectories. One such collision, dubbed Gaia Enceladus, occurred roughly 10 billion years ago and contributed a significant fraction of the stars in our galaxy's halo. Historians still argue about whether the Milky Way grew primarily through such mergers or through gradual gas accretion, forming stars in place over cosmic time. Gaia data supports a picture where both processes matter. The inner galaxy, the bulge and bar, formed early and quickly. The outer disk grew more slowly, fed by infalling gas and occasional snacks of smaller galaxies. The halo, that diffuse sphere of ancient stars surrounding everything, is largely debris from cannibalized companions. For the question of galactic size, Gaia provides the most reliable measurements to date. The stellar disk extends roughly 100,000 light-years in diameter, possibly a bit less depending on where you draw the boundary. The thickness varies. The thin disk containing most of the gas and young stars spans about 1,000 light-years vertically, while the thick disk, older and puffier, reaches 2 to 3 times that height. Beyond these components, the stellar halo stretches thinly outward, its outermost stars detected at distances exceeding 500,000 light-years from the galactic centre. One quirky finding from Gaia involves the galaxy's warp. The Milky Way's disk is not perfectly flat but slightly bent, like a vinyl record left in the sun. This warp has been known for decades from hydrogen observations, but Gaia shows it extends into the stellar distribution as well. The cause remains debated: gravitational interactions with satellite galaxies, infalling dark matter, or some combination thereof. Your platform drifts alongside Gaia as it continues its patient work, scanning the sky again and again, refining distances, uncovering hidden structure. The mission is scheduled to continue through at least the mid-2000s, with each data release expected to sharpen the picture further. Armed with Gaia's measurements, astronomers can now state with confidence that the Milky Way is a large spiral galaxy, but not the largest in its local neighbourhood. That honour belongs to a rival visible to the naked eye on a clear night, a fuzzy smudge in the constellation Andromeda that Hubble used to settle the great debate nearly a century ago. You drift toward a faint glow hanging in the autumn sky, a smudge of light that ancient observers mistook for a nebula, a cloud of gas within our own galaxy. This is Andromeda, also designated M31, and it is the nearest large galaxy to the Milky Way. At roughly 2.5 million light-years distant, it is so far that the light reaching your eyes tonight left before modern humans existed, before our ancestors had learned to chip stone tools or paint on cave walls. Yet in cosmic terms, Andromeda is a close neighbour, close enough that its gravity tugs on us, pulling our two galaxies toward an eventual collision that will reshape everything we know about galactic structure. Comparing the Milky Way to Andromeda is a humbling exercise, the kind of comparison that makes you want to sit down with a strong drink and reconsider your assumptions. Andromeda is bigger. Estimates vary depending on which component you measure and which survey you trust. But most analyses agree that Andromeda's stellar disk spans at least 120,000 light-years, perhaps as much as 150,000, or even more when you include the faint outer regions. Compare that to the Milky Way's roughly 100,000 light-years, and you begin to see the problem. We're not the biggest kid on the block. We're not even close. Andromeda also contains more stars, roughly 1 trillion compared to our 2 to 400 billion. That is a factor of 3 to 5, depending on whose estimates you believe, and it represents an enormous difference in stellar population. Imagine 2 cities, one with 1 million residents and one with 300,000. Both are substantial, but one clearly dominates regional politics. Andromeda is the dominant city. We are the respectable suburb that likes to pretend it is more important than it actually is. The mass comparison is equally unflattering. For decades, astronomers assumed our galaxy held its own against Andromeda, perhaps even slightly exceeding it in total mass when you included the dark matter halo. This assumption made the Milky Way seem respectable, the co-equal partner in a local gravitational dance. 2 giants circling each other, neither clearly superior, destined to merge as equals. It was a comforting narrative, and like many comforting narratives, it turned out to be wrong. Recent measurements have revised this picture dramatically. Using data from Gaia and from observations of satellite galaxies orbiting the Milky Way, astronomers now estimate our galaxy's total mass at roughly 1 trillion solar masses. That sounds impressive until you learn that Andromeda's mass, measured using similar techniques, lands closer to 1.5 trillion solar masses. We are not equals. We are the smaller sibling, and by a significant margin. This matters because mass determines gravitational influence. the Milky Way and Andromeda are falling toward each other at roughly 110 kilometers per second, a collision expected in about 4 to 5 billion years. When that collision occurs, the more massive galaxy will dominate the gravitational interaction, shaping the merger remnant more strongly than the smaller one. In very rough terms, Andromeda will absorb us rather than the reverse. We will contribute our stars and gas to a new combined system, but Andromeda's structure will form the backbone. It is like two companies merging where one has 3 times the market capitalization. Technically a merger, functionally an acquisition. Historians still argue about when astronomers first recognized Andromeda as a distinct galaxy, rather than a nebula within the Milky Way. Hubble's 1924 Cepheid observations provided the definitive evidence, the smoking gun that settled the great debate, but suspicions predated him by decades. Lord Rosse, observing with his massive Leviathan of Parsonstown Telescope in Ireland in the 1840s, noted Andromeda's spiral structure, a feature difficult to explain if it were merely a gas cloud. Why would gas arrange itself in such a pattern? The spiral suggested rotation, structure, something more complex than a simple nebula. Heber Curtis, debating Harlow Shapley in 1920, cited Andromeda's dimmed novae as evidence of great distance. Novae within the Milky Way reach certain peak brightnesses. Novae in Andromeda appeared far dimmer, suggesting they were much farther away. If Andromeda lay within our galaxy, its novae should appear comparably bright. They did not. The intellectual groundwork was laid long before Hubble aimed his telescope at the fuzzy smudge and found the kephas that clinch the argument. One quirky detail about Andromeda involves its satellite galaxies. Just as the Milky Way is orbited by smaller companions like the Large and Small Magellanic Clouds, Andromeda has its own entourage of gravitationally bound dwarfs. 2 of these, M32 and M110, are visible in backyard telescopes as fuzzy blobs near Andromeda's core. M32 is particularly interesting because it appears to have passed through Andromeda's disk at some point, its structure distorted by the encounter. It is a galaxy that survived a collision with a larger galaxy, battered but intact. Other Andromeda satellites are so faint they escape detection, until recent surveys push the limits of observational sensitivity. The count of Andromeda's satellites now exceeds 30, with more candidates awaiting confirmation. Each of these tiny galaxies has its own story, its own formation history, its own population of ancient stars. Some will eventually be consumed by Andromeda, others may survive for billions of years as independent systems. For our purposes tonight, Andromeda serves as a mirror. By studying another spiral galaxy from the outside, astronomers can test ideas about galactic structure that are difficult to verify from within the Milky Way. We cannot step outside our galaxy to photograph it, cannot see its spiral arms from above, cannot measure its diameter with a ruler. But we can photograph Andromeda and compare its features to what we know of our own. This comparison reveals that spiral galaxies vary widely in size, mass and structure, and that the Milky Way falls somewhere in the middle of the distribution. We are not the smallest spiral by any means, but we're certainly not the largest either. We are, cosmically speaking, average. This averageness is consistent with the Copernican principle, the philosophical assumption that humanity does not occupy a special or privileged position in the universe. We orbit an ordinary star in an ordinary part of an ordinary galaxy, in an ordinary group of galaxies in what appears to be an ordinary corner of the cosmos. Every attempt to claim special status has been refuted by observation, and the Andromeda comparison is simply the latest chapter in that ongoing humiliation. Your platform turns away from Andromeda now, back toward the milky band of our own galaxy stretching across the sky. Somewhere below that glow lies the supermassive black hole at the galactic centre, the spiral arms traced by young stars and gas, the dark matter halo extending invisibly into the void. This is your home, modest in comparison to some neighbours, vast beyond comprehension by human standards, and surrounded by companions both large and small. You descend now into the darkness beyond the Milky Way's visible disk, drifting toward faint smudges of light that barely register against the cosmic background. These are dwarf galaxies, tiny companions orbiting our own, gravitationally bound yet distinct, like sparrows circling an eagle or moons orbiting a planet. They are easy to overlook, easy to dismiss as cosmic footnotes, but they hold secrets about galactic evolution that the Milky Way itself cannot reveal. The most famous of these companions are the large and small Magellanic Clouds, visible from the southern hemisphere as detached patches of the Milky Way, named after the explorer Ferdinand Magellan, whose crew noted them during their circumnavigation of the globe in the early 16th century. These clouds are irregular dwarf galaxies containing billions of stars each. They are not spirals like the Milky Way or Andromeda. They lack the organised structure, the neat arms, the central bulge. Instead, they appear chaotic, their stars scattered without obvious pattern, their gas distributed in clumps and filaments. The large Magellanic Cloud, about 14,000 light-years across, lies roughly 160,000 light-years from the galactic centre. It is the third closest galaxy to the Milky Way, after the Sagittarius Dwarf and the Canis Major Dwarf, both of which are currently being torn apart by tidal forces. The large Magellanic Cloud is substantial enough to resist immediate destruction, though its shape has been distorted by gravitational interactions. One side appears stretched, pulled toward our galaxy by invisible tidal fingers. The small Magellanic Cloud, smaller and farther, orbits at about 200,000 light-years. It too shows signs of gravitational harassment, its structure elongated along the line connecting it to the Milky Way. Both clouds are close enough that their gravity interacts with our galaxy, and our gravity interacts with them. This mutual tugging creates streams of gas trailing behind the clouds, material stripped from their outer regions and left to drift through intergalactic space. The Magellanic Stream, a river of hydrogen stretching over 100 degrees across the sky, traces the orbital path of these companions. But the Magellanic Clouds are giants among dwarfs. The Milky Way's fainter satellites are far more numerous and far harder to detect. The Sagittarius Dwarf Elliptical Galaxy, discovered in 1994 on the far side of the galactic centre, is currently being ripped apart by tidal forces. Its stars are streaming into the Milky Way's halo, forming a great arc that wraps nearly around the entire galaxy. In a few 100 million years, nothing will remain of Sagittarius as a distinct entity. Its stars will be fully absorbed into our population, their origins traceable only through careful chemical analysis. The Ursa Minor Dwarf and Draco Dwarf, discovered in the 1950s, contain only a few 100,000 stars each. They are so diffuse, so spread out across the sky, that identifying them requires statistical analysis rather than simple visual inspection. You cannot point a telescope at the Ursa Minor Dwarf and see a clear concentration of stars. You can only detect a subtle excess against the background, a region where stars are slightly more common than expected. And then there are the ultra-faint dwarfs discovered since 2005, galaxies so faint they challenge the very definition of the term. These objects contain just a few thousand stars spread across regions larger than some globular clusters. Their total luminosity is less than that of a single bright star. Without sophisticated surveys and careful data analysis, they would be invisible, lost in the noise of the Milky Way's own stellar population. These ultra-faint dwarfs raise interesting questions about what constitutes a galaxy. Traditionally, galaxies are distinguished from star clusters by the presence of dark matter. Galaxies are embedded in dark matter halos, while star clusters are not. The ultra-faint dwarfs appear to have dark matter based on the motions of their stars, which move faster than their visible mass alone could explain. But they contain so few stars that their luminosity rivals some open clusters in the Milky Way's disk. Naming conventions strain under the weight of these borderline cases. Historians still argue about the total number of satellite galaxies orbiting the Milky Way. The count has climbed steadily as surveys probed deeper and algorithms improved. In 2000, the known count stood at about 11, a number that had remained stable for decades. By 2010, it had doubled. By 2023, it exceeded 60, with additional candidates awaiting confirmation. Simulations of galaxy formation in a dark, matter-dominated universe predict hundreds of dark matter subhalos orbiting the Milky Way, most of them potentially hosting tiny galaxies. Many satellites likely remain undiscovered, either because they contain no stars at all, or because their stars are too few and faint to detect with current technology. One quirky aspect of satellite galaxies is what they reveal about dark matter physics. The distribution and properties of satellites should match predictions from cosmological simulations, but for years they did not. This mismatch, called the missing satellite problem, suggested either that dark matter behaves differently than expected, or that our understanding of galaxy formation is incomplete. The problem had two aspects. Simulations predicted more satellites than were observed, and the observed satellites were less centrally concentrated than simulations suggested. Recent discoveries of ultra-faint dwarfs have eased the tension somewhat. The observational census was simply incomplete. As surveys improved, the satellite count rose toward theoretical predictions, but discrepancies remain. Some satellites orbit in a thin plane rather than the spherical distribution simulations predict, a pattern called the plane of satellites problem. Others are more massive than expected for their luminosity, suggesting their dark matter halos are denser than models allow. Dark matter, despite its gravitational dominance, continues to defy easy understanding. For the question of galactic size, satellite galaxies complicate matters significantly. If you define the Milky Way's boundary as the region within which its gravity dominates, you must include objects far beyond the stellar disk. The most distant known satellites lie over 1 million light-years from the galactic centre, at the very edge of the Milky Way's gravitational sphere of influence. These objects are still falling toward us, their orbits not yet complete, their futures tied to our galaxy's mass. You settle back into the present moment, hovering over a research institution, where astronomers are finalizing the latest measurements of the Milky Way's size. On their screens, data streams from Gaia, from radio surveys, from infrared telescopes that peer through the dust obscuring the galactic centre. The numbers are converging toward a consensus, and the picture they paint is clearer than at any point in human history. The Milky Way's stellar disk, the flattened region containing most of the visible stars, measures approximately 100,000 light-years in diameter. This number has been revised downward over the decades, a gradual shrinkage that reflects improved measurement techniques rather than any physical change in the galaxy itself. Earlier estimates, often relying on indirect methods or incomplete surveys, placed the disk at up to 180,000 light-years. Some particularly optimistic assessments in the mid-20th century suggested even larger values, fueled by calibration errors in the Cepheid distance scale, and by the still unrecognized effects of interstellar dust absorption. Gaia's parallax measurements, combined with spectroscopic distances to red giant stars far from the Sun, suggest the true extent is closer to 100,000 light-years, possibly slightly less depending on where you draw the boundary. The most recent analyses place the disk diameter between 90,000 and 100,000 light-years, a range narrow enough to inspire confidence, yet wide enough to acknowledge remaining uncertainties. This shrinkage might seem disappointing at first, like discovering your new apartment is smaller than the listing claimed, or learning that your impressive job title does not come with the salary you expected. But the number itself is less important than the precision. For the first time in history, astronomers can state the galaxy's size with genuine confidence, backed by billions of direct distance measurements rather than extrapolations from limited samples. We may have a smaller galaxy than we thought, but we know its size far better than any previous generation could have imagined. The disk's thickness is equally well constrained by modern observations. The thin disk, home to the gas, dust and young stars that trace the spiral arms, extends about 1,000 light-years above and below the galactic plane. This is the region where star formation occurs, where nebulae glow with the light of newborn suns, where the material for future generations of stars accumulates. The thick disk, populated by older, metal-poor stars that formed earlier in the galaxy's history, puffs out to roughly 3,000 light-years above and below the midplane. These older stars have had billions of years to be scattered by gravitational encounters, their orbits becoming more eccentric, their vertical excursions more pronounced. Beyond these disk components, the stellar halo stretches thinly into the surrounding space. The halo is not a disk at all, but a roughly spherical distribution of ancient stars, globular clusters, and debris from disrupted satellite galaxies. Its most distant members have been detected at several 100,000 light-years from the galactic center, lonely outposts at the edge of the Milky Way's gravitational influence. Historians still argue about when the Milky Way's size estimate stabilized into its current form. Through much of the 20th century, values fluctuated wildly, driven by competing calibration methods and incomplete data. Shapley's 1920 estimate of 300,000 light-years was too large by a factor of 3, inflated by errors in the Cepheid distance scale and by his lack of awareness of interstellar absorption. Mid-century estimates around 100,000 light-years were closer to modern values, but remained uncertain, with error bars large enough to accommodate significant revision. Only with the Hippocos mission in the 1990s and then Gaia in the 2010s did the numbers settle into their current range with genuine precision. One quirky complication involves the galaxy's edge, or rather, the absence of a clear edge. Unlike a planet or a star, the Milky Way does not have a sharp boundary where material suddenly ends. The stellar density decreases smoothly with distance from the galactic center, following mathematical profiles that approach but never quite reach zero. Where you draw the edge depends entirely on your detection threshold and your definition of what counts as part of the galaxy. If you can see fainter stars, the galaxy appears larger. If your instruments are less sensitive, it appears smaller. This is not a flaw in the measurements, but a fundamental feature of galaxies. They fade rather than end, their boundaries statistical rather than physical. Another complication involves the different stellar populations. The thin disk, thick disk, and halo contain different types of stars, formed at different times under different conditions. The thin disk is rich in heavy elements, metals forged in generations of stellar deaths and supernova explosions. The thick disk is chemically intermediate, its stars formed when the galaxy was younger and less enriched. The halo is ancient and metal poor, its stars formed from nearly pristine hydrogen and helium in the early universe. Each population traces a slightly different structure, so asking for the galaxy's size requires specifying which stars you mean. The thin disk is smaller than the thick disk, which is smaller than the halo. All three numbers are correct. None tells the complete story. For popular purposes, the commonly quoted figure is around 100,000 light-years for the diameter of the stellar disk. This is the number you will find in textbooks, museum exhibits, and science documentaries. It represents a reasonable average, acknowledging that the exact boundary is fuzzy and the thickness varies with radius. When someone asks how big the Milky Way is, this is the number astronomers typically provide. What this number does not capture is the dark matter halo, extending far beyond the stellar disk, invisible to every telescope ever built. The halo contains the majority of the galaxy's mass, yet contributes almost nothing to its visible appearance. Including the dark matter halo, the Milky Way's gravitational sphere of influence reaches over 1 million light-years, touching the orbits of its most distant satellite galaxies and overlapping with the halos of neighbouring systems. You drift outward now, past the stellar disk with its spiral arms and star-forming regions, into the realm of the halo. The stars here are sparse, separated by light-years of empty space, their ancient light barely distinguishable from the cosmic background radiation that fills the universe. This is the galactic halo, a ghostly suburb surrounding the bright city centre, populated by the oldest residents and the debris of long-dead companions. The halo is not a single structure but several overlapping populations, each with its own history and characteristics. The inner halo, extending perhaps 50,000 light-years from the galactic centre, contains the globular clusters, those dense spherical swarms of ancient stars that Harlow Shapley used a century ago to deduce our position within the galaxy. Roughly 150 globular clusters orbit the Milky Way, relics from the galaxy's earliest days when conditions favoured the formation of tightly bound stellar systems. Their stars are among the oldest known, some approaching 13 billion years, formed when the universe itself was young and galaxies were just beginning to assemble. The globular clusters orbit the galactic centre on highly elliptical paths, plunging deep into the inner regions before swinging back out into the halo. Their orbits are not confined to the disk plane. They approach from all angles, a swarm of bees rather than a flat ring. This three-dimensional distribution is what allowed Shapley to recognise that the clusters traced a structure much larger than the visible disk, centred not on the Sun but on a point in the direction of Sagittarius. Beyond the globular clusters, the outer halo stretches thinly into the void. Individual stars have been detected at distances exceeding 500,000 light-years from the galactic centre, so faint and isolated that their membership in the Milky Way was controversial until radial velocity measurements confirmed they are gravitationally bound. These outermost halo stars are not orbiting in neat circles. Their trajectories are elongated ellipses that take billions of years to complete, falling toward the galactic centre, swinging around it, and climbing back out to the distant reaches before repeating the cycle. The stellar halo contains only about 1% of the Milky Way stars, a negligible fraction by number. You could remove the entire halo and the galaxy would look almost identical, its spiral arms unchanged, its rotation curve barely affected. But the halo's extent far exceeds the disks, complicating any simple definition of galactic size. If you count stars and ask where most of them live, the galaxy is about 100,000 light-years across. If you trace the farthest gravitationally bound stars and ask how far the Milky Way's influence reaches, the answer may exceed 500,000 light-years. Historians still argue about the halo's origin, a debate that has intensified as data from Gaia and other surveys has accumulated. One traditional view held that halo stars formed in place, condensing from primordial gas before the disk assembled, their random orbits reflecting the chaotic conditions of early galaxy formation. This in situ formation model predicted a relatively smooth halo with gradually changing properties as you moved outward from the centre. The competing view held that halo stars were largely captured from smaller galaxies that fell into the Milky Way and were torn apart by tidal forces. In this accretion model, the halo is not a smooth sphere but a tangle of debris, the archaeological record of the galaxy's violent assembly. Different streams of stars would have different chemical compositions and orbital properties, reflecting their distinct origins in now destroyed companions. Gaia data has strongly supported the accretion interpretation. The stellar halo is not smooth at all. It contains coherent streams of stars tracing the paths of long-dead satellite galaxies. The most dramatic example is Gaia Enceladus, also called the Gaia Sausage, a substantial galaxy that collided with the Milky Way roughly 10 billion years ago. Its stars, identified by their distinct chemical signatures and their highly eccentric orbits, now populate much of the inner halo. The collision was violent enough to heat the Milky Way's existing disk, puffing it up and contributing to the formation of the thick disk component. Other streams mark the graves of other victims. The Sagittarius stream wraps nearly around the entire galaxy, debris from the ongoing destruction of the Sagittarius dwarf galaxy. Fainter streams, some only recently identified, trace earlier mergers whose satellite galaxies have been completely absorbed. The halo is a graveyard and a history book, its contents revealing the Milky Way's appetite for smaller companions and its method of growth through cosmic cannibalism. One quirky feature of the halo is its shape. Rather than a perfect sphere, it appears to be slightly oblate, flattened in the same direction as the disk. The degree of flattening varies with distance. The inner halo is more spherical, while the outer halo shows greater flattening. This shape likely reflects the distribution of dark matter, which dominates the halo's mass and dictates its gravitational potential. Stars orbiting within a flattened dark matter halo will themselves trace a flattened distribution, their paths shaped by the invisible scaffold surrounding them. The dark matter halo extends even farther than the stellar halo, though its boundaries are impossible to observe directly. Simulations suggest it may reach 1 to 2 million light-years before blending into the intergalactic medium, the thin gas and dark matter filling the spaces between galaxies. But without direct detection of dark matter particles, these estimates remain theoretical, inferred from gravitational effects rather than observed emission. For you, drifting through this sparse realm, the halo feels less like a place and more like a memory. The stars here are old, their nuclear fires dimmed by billions of years of steady burning. Some have exhausted their hydrogen and swelled into red giants before shedding their outer layers. Others have collapsed into white dwarfs, fading slowly toward invisibility as they radiate away their residual heat. A few, born with masses large enough to explode as supernovae, have already done so, seeding the halo with heavy elements that will eventually fall back into the disk and participate in new generations of star formation. Your platform turns back toward the familiar glow of Andromeda, hanging in the distance like a mirror image of home. You've already compared these two galaxies in broad strokes, but the comparison deserves deeper examination because it shapes our understanding of where the Milky Way stands in the cosmic hierarchy and what its future holds. Andromeda's dominance over the Milky Way is not merely a matter of bragging rights between neighbouring galaxies. It has practical consequences for the merger that will occur billions of years from now, when these two spirals fall together and combine into a single elliptical system. In any galactic merger, the more massive partner contributes more to the final structure. Its central black hole tends to dominate the merged core. Its stars form the backbone of the new system. Its dark matter halo shapes the gravitational potential that governs all future evolution. When the Milky Way and Andromeda merge, Andromeda will be that dominant partner. Our galaxy will contribute its stars, its gas, its dark matter to the combined system, but we will be the junior participant. The merger remnant, sometimes called Milkomeda or Milkdromeda by astronomers with a taste for portmanteau names, will bear Andromeda's stamp more strongly than ours. This is not a merger of equals, but something closer to an acquisition, even if both parties are destroyed in the process. The mechanics of the collision are worth understanding because they illustrate how galaxies interact at the larger scales. Right now, Andromeda and the Milky Way are approaching each other at roughly 110 kilometers per second. This sounds fast, and by human standards it is, but galaxies are so vast and so far apart that the collision will take billions of years to complete. The first close approach is expected in about 4 to 5 billion years, roughly the same timescale on which the Sun will exhaust its hydrogen fuel and begin expanding into a red giant. During that first approach, the two galaxies will not collide head-on like cars in a crash. Instead, they will pass through each other, their stars so widely spaced that direct stellar collisions are essentially impossible. Stars are tiny compared to the distances between them. Even in the densest regions of a galaxy, two stars passing within a light year of each other would be a remarkable near miss. What will happen instead is gravitational disruption. Tidal forces will distort both galaxies, stretching them into elongated shapes, tearing stars from their orbits, triggering bursts of star formation as gas clouds compress and collapse. After the first passage, the two galaxies will swing back toward each other, pulled by their mutual gravity. They will pass through each other again, losing more energy to dynamical friction, their orbits decaying. Over hundreds of millions of years, they will make multiple passes, each one drawing them closer, until finally they settle into a single merged system. The spiral structure of both galaxies will be destroyed, their ordered rotation replaced by the random stellar motions characteristic of elliptical galaxies. Historians still argue about when astronomers first predicted this merger. The relative motion of Andromeda toward the Milky Way, its blue shift in spectroscopic observations, has been known since the early 20th century. But translating that velocity into a collision prediction required understanding the total mass of both systems and the geometry of their approach. Early estimates were uncertain. More recent analyses using Gaia data to measure Andromeda's transverse motion have refined the prediction, confirming that a collision is essentially certain rather than merely probable. One quirky detail about the Andromeda-Milky Way merger involves the Sun's fate. When the collision occurs, our solar system will still exist, though the Sun will be entering its final stages of evolution. The merger itself poses little direct threat to any planets that might still orbit the dying Sun. The probability of another star passing close enough to disrupt planetary orbits is negligible, even during the chaotic early phases of the merger. What will change is the view from those planets. Instead of a neat spiral galaxy spanning the sky, observers would see a chaotic mess of tidal tails, star streams, and distorted structures gradually settling into an elliptical glow. The merger will also affect the two galaxies' satellite populations. Some satellites currently orbiting the Milky Way will be captured by Andromeda. Some of Andromeda's satellites will end up orbiting the combined remnant. Others will be flung out into intergalactic space by gravitational slingshots, ejected from the system entirely. The Magellanic Clouds, if they have not already merged with the Milky Way by then, might be torn from their current orbits and sent on new trajectories. For the question of galactic size, the Milky Way-Andromeda comparison provides important context. Our galaxy is not tiny by any measure. It is a substantial spiral containing hundreds of billions of stars capable of supporting complex chemistry, planetary systems, and perhaps life. But among the local giants, we rank second. Andromeda outmasses us, outshines us, and will ultimately absorb us. This ranking is unlikely to change through any process short of the merger itself, which will end both galaxies' independent existence. The comparison also reminds us that galaxy sizes vary enormously across the universe. Andromeda and the Milky Way are both large spirals, members of a category that represents only a small fraction of all galaxies. Most galaxies are dwarfs, containing millions or billions of stars rather than hundreds of billions. At the other extreme, giant elliptical galaxies in the centres of galaxy clusters can contain trillions of stars, dwarfing both Andromeda and the Milky Way by factors of 10 or more. In that broader context, our galaxy is neither particularly large nor particularly small. It is average, a cosmic Goldilocks zone of galactic mass and size. This averageness, as noted before, is philosophically significant. The Copernican principle suggests we should not expect to occupy a special position in the universe, and our galaxy's middling rank supports that expectation. We're not the biggest, not the smallest, not the oldest, not the youngest. We're ordinary, and ordinary turns out to be an interesting place to be. You descend back toward the Milky Way now, drawn toward the faint companions orbiting its disk like pilot fish around a whale or moons around a planet. These dwarf galaxies deserve closer attention because they reveal not just the Milky Way's current state, but its history and future, the processes of growth and destruction that have shaped our galaxy over billions of years. The Milky Way has consumed smaller galaxies before. The evidence is written in the stellar halo, in streams of stars tracing the paths of dismembered companions, in chemical signatures that betray foreign origins. This is not ancient history in the sense of being safely concluded. It is an ongoing process, with victims currently being digested and future victims already falling toward their doom. The Sagittarius dwarf galaxy provides the most dramatic example of active galactic cannibalism. Discovered in 1994 on the far side of the galactic centre, Sagittarius is currently being ripped apart by tidal forces, its stars stretched into a vast arc that wraps nearly around the entire Milky Way. The stream of debris extends over 200 degrees across the sky, a ghostly river of stars marking where Sagittarius has travelled and what it has lost along the way. Sagittarius is not simply orbiting the Milky Way in a stable configuration. It is falling through our galaxy's disk, losing stars with each passage, gradually being absorbed into the halo population. In perhaps 100 million years, nothing recognizable will remain of Sagittarius as a distinct entity. Its stars will have fully merged with ours, indistinguishable except through careful chemical and kinematic analysis. The galaxy that once existed independently will become a footnote in the Milky Way's archaeological record. Other streams tell older stories. Gaia Enceladus, mentioned earlier, was a substantial galaxy that collided with the Milky Way roughly 10 billion years ago, when our galaxy was still young and forming. The collision was not a gentle merger, but a violent event, massive enough to heat the existing disk and contribute to the formation of the thick disk component. Gaia Enceladus contributed perhaps 500 million solar masses to the Milky Way, a significant fraction of the current halo population. Identifying Gaia Enceladus required the precise stellar motions and chemical abundances that Gaia provides. Its stars share distinct orbital properties, moving on highly eccentric paths that take them plunging through the inner galaxy before climbing back out into the halo. They also share chemical signatures, patterns of elemental abundances that differ subtly from native Milky Way stars and reflect the chemical evolution of their original host galaxy. By combining these kinematic and chemical clues, astronomers can identify Gaia Enceladus debris, even though the original galaxy no longer exists as a recognizable structure. Historians still argue about how many galaxies the Milky Way has consumed over its lifetime. Estimates range from a handful of major mergers comparable to Gaia Enceladus to dozens of minor accretions involving smaller dwarf galaxies. The total mass accreted varies accordingly, with some models suggesting the Milky Way has roughly doubled its mass through mergers, while others propose more modest growth. The uncertainty reflects the difficulty of disentangling ancient debris from the native population, especially as time erases the orbital signatures that distinguish captured stars. One quirky aspect of galactic cannibalism is its fundamental asymmetry. Large galaxies grow by eating smaller ones, not the reverse. Dark matter halos provide the gravitational scaffolding that makes this possible. The more massive the halo, the more satellites it can capture and the faster it grows. This rich-get-richer dynamic ensures that the cosmic hierarchy is relatively stable over time, with giant galaxies dominating their local environments for billions of years, while dwarf galaxies gradually disappear into their maws. For the Milky Way, the future holds more consumption. The large and small Magellanic Clouds are not in stable orbits around our galaxy. They are slowly spiralling inward, losing energy to dynamical friction as they plough through the dark matter halo. Dynamical friction is a subtle effect, arising from the gravitational wake that a moving object creates in the surrounding medium. As a satellite galaxy moves through dark matter, it pulls material behind it, creating a trailing over density that tugs backward on the satellite and gradually slows its motion. Over billions of years, this friction causes orbits to decay, bringing satellites closer to the central galaxy. In perhaps 2 billion years, the Large Magellanic Cloud will make its first close passage through the Milky Way's disk, an event that may trigger star formation in both systems. Eventually, possibly before the Andromeda collision, the Magellanic Clouds will merge fully with the Milky Way, adding their stars and gas to our population. Our galaxy will grow slightly larger, slightly more massive, slightly richer in heavy elements. This raises an interesting philosophical question about galactic size. If the Milky Way absorbs the Magellanic Clouds, does it become larger? The answer depends on how you measure. The total mass and star count will certainly increase, but the disk diameter may not change significantly. The absorbed stars will spread throughout the existing structure rather than extending the boundaries outward. Some will settle into disk orbits, contributing to the thin or thick disk populations. Others will join the halo, their eccentric orbits reflecting their recent capture. The galaxy grows without necessarily expanding. The smallest satellites face different fates. The ultra-faint dwarfs, with their minuscule masses and sparse stellar populations, are vulnerable to tidal disruption even at relatively large distances from the Milky Way. Some may be destroyed before they ever reach the disk, their stars scattered into the halo by tidal forces. Others may survive for billions of years, their compact dark matter halos shielding them from gravitational stress. The outcome depends sensitively on their orbital parameters and internal structure, properties that remain poorly constrained for the faintest systems. Time accelerates as your platform rises higher above the galactic plane, the Milky Way's spiral arms blurring below like the spokes of a spinning wheel. You watch the galaxy evolve, its shape shifting over timescales that make human history seem like the blink of an eye. The collision with Andromeda is the main event on the cosmic calendar, but it is not the only transformation awaiting our stellar home. Before that dramatic merger, the Milky Way will continue its quieter evolution, shaped by internal processes and interactions with its satellite companions. The spiral arms will wind and reform, their patterns driven by density waves that propagate through the disk like ripples in a pond. Star formation will continue in the arms, though at a declining rate as the galaxy's gas supply gradually depletes. New stars will ignite, live their lives, and die, enriching the interstellar medium with heavy elements that will be incorporated into future generations. One process already underway is the warp and flare of the galactic disk. If you could see the Milky Way edge-on from the outside, you would notice that it is not perfectly flat. The outer disk bends upward on one side and downward on the other, like a vinyl record left in the sun or a hat brim curled by wear. This warp was first detected decades ago through observations of the hydrogen gas distribution and has since been confirmed in the stellar populations by Gaia. The cause of the warp remains debated among astronomers. One leading hypothesis involves gravitational interaction with the Magellanic Clouds, whose combined mass is substantial enough to tug on the outer disk and distort its shape. As the clouds orbit the Milky Way, the gravitational influence shifts, causing the warp to precess slowly over hundreds of millions of years. Another hypothesis invokes the dark matter halo, suggesting that the halo is not spherical but slightly tilted relative to the disk, creating torques that bend the outer regions. A third possibility involves resonances within the disk itself, wave-like disturbances that propagate outward and lift the disk plane as they go. The disk also flares at its edges, growing thicker with increasing distance from the galactic centre. Near the Sun, the thin disk is about 1,000 light-years thick. In the outer galaxy, that thickness may double or triple, the stars distributed more broadly above and below the midplane. This flaring reflects the weaker gravitational restoring force in the outer regions. Stars can wander farther from the plane before the galaxy's gravity pulls them back. Historians still argue about whether the Milky Way's spiral arms are long-lived features or transient patterns that come and go over cosmic time. Density wave theory, proposed in the 1960s by C.C. Lin and Frank Hsu, suggests the arms are self-sustaining compression waves that rotate through the disk at a constant pattern speed. In this view, the arms persist for billions of years, even though individual stars continuously move in and out of them. The arms are like traffic jams. The cars change, but the jam stays in place. Alternative models treat the arms as transient structures, caused by gravitational instabilities, interactions with satellites, or random fluctuations in the stellar distribution. In these models, arms form, persist for a few 100 million years, and then dissolve, replaced by new arms in different locations. The Milky Way's current spiral pattern would be a snapshot of an ever-changing structure, not a permanent feature of the galaxy. Gaia data may eventually resolve this debate by providing precise ages for stars in and near the spiral arms. If the arms are long-lived, stars of all ages should be found within them. If the arms are transient, the stellar age distribution should show signatures of arm formation and dissolution. Current data hints at complexity, with different arm segments showing different properties, but definitive conclusions remain elusive. One quirky possibility involves the Milky Way's ultimate fate long after the Andromeda merger is complete. The combined elliptical galaxy will continue evolving, gradually expelling its remaining gas through stellar winds and supernovae, ceasing star formation as its fuel supply depletes. The existing stars will age, the brightest ones dying first, leaving behind a population of ever dimmer red dwarfs, white dwarfs, and stellar remnants. Over trillions of years, gravitational encounters between stars will slowly reorganize the galaxy. Occasionally, two stars will pass close enough that one gains energy, while the other loses it. The energetic star may escape the galaxy entirely, ejected into intergalactic space. The slower star sinks toward the center, adding its mass to the growing central concentration. This process, called evaporation, will gradually strip the outer regions of the galaxy while building up the core. Eventually, perhaps hundreds of billions of years from now, only a dense core of black holes, neutron stars, and fading stellar remnants may remain, orbiting a supermassive black hole grown fat from merged companions. The spiral structure you see tonight will be a distant memory, preserved only in whatever records future intelligences might maintain. The Milky Way as we know it is a temporary configuration, a pattern in the cosmic flux, destined to dissolve into something unrecognizable. For the question of galactic size, these evolutionary processes remind us that measurements are snapshots, not eternal truths. The Milky Way was smaller in the past, before it absorbed companions and accumulated gas from the intergalactic medium. It will be unrecognizable in the future, merged with Andromeda and transformed into an elliptical system without spiral arms or a well-defined disk. Size is not a fixed property, but a momentary measurement in an ongoing process of cosmic change. Your platform settles into a contemplative pause, the galaxy spread beneath you like a map drawn without borders. The question that has guided tonight's journey, how small is the Milky Way really, turns out to depend entirely on how you define its edge. This seemingly simple definitional issue has occupied astronomers for decades and remains unresolved, not because of ignorance, but because galaxies genuinely lack sharp boundaries. If you define the galaxy by its visible stars, the commonly cited number is approximately 100,000 light-years in diameter for the stellar disk. This is the figure most people encounter in textbooks, museum exhibits, and popular science documentaries. It represents the extent of the region where stars are densely packed enough to be easily detected, where the spiral arms trace their graceful curves, where the familiar structure of a barred spiral galaxy is apparent to any sufficiently powerful telescope. But visible stars are only part of the story. If you include the stellar halo, that diffuse sphere of ancient stars surrounding the disk, the galaxy expands considerably. The outermost halo stars definitively associated with the Milky Way lie over 500,000 light-years from the galactic centre, so faint and isolated that confirming their membership required careful measurement of their velocities. These stars are gravitationally bound to the Milky Way, orbiting on elongated paths that take billions of years to complete, but their density is so low that calling this region part of the galaxy feels almost metaphorical. If you consider the dark matter halo, the invisible structure that dominates the galaxy's total mass, the size grows larger still. Estimates based on satellite dynamics and cosmological simulations place the halo's virial radius, the distance within which material is gravitationally bound and roughly in equilibrium, at roughly 1 to 2 million light-years. By this definition, the Milky Way encompasses a volume several hundred times larger than the stellar disk alone, a vast sphere of invisible matter containing the visible galaxy like a pearl embedded in amber. Historians still argue about which definition of galactic size is most appropriate, and the answer depends heavily on context. For astronomers studying stellar populations and galactic structure, the stellar disk is the natural choice because it is what telescopes actually observe. For cosmologists modelling galaxy formation and dark matter distribution, the virial radius matters more because it determines gravitational interactions with neighbours and the overall mass budget. One quirky aspect of this definitional debate involves the concept of the virial radius itself. In cosmology, the virial radius is defined somewhat arbitrarily as the distance within which the average density exceeds a certain multiple of the cosmic mean density, typically around 200 times. This definition is mathematically convenient, corresponding roughly to wherein falling material has had time to settle into equilibrium with the existing structure. But it is not a physical boundary in any meaningful sense. Material can and does cross the virial radius in both directions, falling in from the intergalactic medium or being ejected through dynamical processes. The virial radius is also not directly observable. Dark matter cannot be seen, so its distribution must be inferred from gravitational effects. The rotation curves of gas and stars, the motions of satellite galaxies, the gravitational lensing of background light. These methods provide constraints on the total mass and its radial profile, but the exact location of any particular isodensity contour remains uncertain. Different analyses using different data sets and different modelling assumptions can produce virial radius estimates that vary by factors of 2 or more. Another complication involves the distinction between the Milky Way and its immediate environment. Our galaxy does not exist in isolation, but is embedded in a cosmic web of dark matter filaments, connecting it to neighbouring galaxies. Material flows along these filaments, feeding the galaxy with fresh gas and dark matter over cosmic time. Where does the Milky Way end and the cosmic web begin? There is no sharp transition, no fence marking the property line. The galaxy blends smoothly into its surroundings, its gravitational influence extending far beyond any reasonable definition of its edge. This lack of a clear boundary might seem like a failure of precision, an embarrassing vagueness in an otherwise quantitative science, but it reflects a genuine feature of galaxies as physical objects. Unlike planets, which have solid surfaces, or stars, which have photospheres where opacity increases sharply, galaxies are collections of objects held together by gravity. Their extent is defined by that gravitational binding which fades smoothly with distance rather than ending abruptly. Asking for the exact size of a galaxy is like asking for the exact size of a cloud. You can give a reasonable answer, but the edges will always be fuzzy. For practical purposes, most astronomers use the stellar disk diameter when discussing galactic size in popular contexts, and the virial mass or virial radius when doing technical calculations involving gravity and cosmology. Both approaches are valid. Neither captures the full complexity of what a galaxy actually is. The Milky Way is simultaneously 100,000 light-years across and 1,000,000 light-years across, depending on which question you're asking and which component you consider relevant. This dual standard can confuse non-specialists who reasonably expect a single number to describe how big the galaxy is. But the confusion reflects a deeper truth about astronomical objects. They are not as simple as everyday experience suggests. A galaxy is not a thing in the same way a chair is a thing. It is a process, a concentration of matter flowing through space and time, its boundaries defined by statistical decrements rather than physical barriers. The human psyche does not handle cosmic insignificance gracefully. You have journeyed tonight through the history of galactic measurement, watching the Milky Way shrink in relative importance with each discovery, each refinement, each comparison to neighbours we did not know existed. The pattern is relentless and humbling, a progressive demotion that began centuries ago and shows no signs of stopping. First, Copernicus moved Earth from the centre of the solar system. The Sun, not our planet, anchored the cosmic dance, with Earth reduced to one of several worlds orbiting the central fire. This was jarring enough to provoke ecclesiastical condemnation and decades of controversy. The idea that we might not be at the centre of everything was philosophically disturbing in ways that are hard to recapture now that heliocentrism is taught to children. Then Shapley moved the Sun from the centre of the galaxy. Using globular clusters as tracers, he demonstrated that our solar system lies roughly 26,000 light-years from the galactic core, orbiting in an unremarkable region of a spiral arm. We were not even centrally located within our own stellar city, let alone the universe at large. The Copernican demotion gained a second chapter. Then Hubble revealed other galaxies, proving that the Milky Way is not the entire cosmos, but merely one galaxy among countless others. The spiral nebulae that astronomers had debated for decades turned out to be island universes in their own right. Some larger than ours, some smaller, scattered through a universe far vaster than anyone had imagined. Our galaxy went from being everything to being a tiny fraction of everything. Then Rubin exposed dark matter, demonstrating that the visible stars and gas we can observe constitute only a small fraction of the total mass. The Milky Way is not even mostly made of stuff we can see. Its dominant component is invisible, detectable only through gravitational effects, mysterious in composition and origin. We are passengers on a ship whose hull we cannot perceive. And now, the latest measurements confirm that our galaxy is smaller than we thought, smaller than our nearest large neighbour, average among spirals, unremarkable in every dimension we can quantify. The Milky Way is not the biggest kid on the block, it is not the most massive, It is not specially positioned within the local group or the larger cosmic structure. It is ordinary, and ordinary keeps getting more ordinary with each passing decade. Historians still argue about whether this pattern of demotion constitutes a genuine principle or merely reflects the human tendency to assume specialness in the absence of evidence. The Copernican principle, as it is sometimes called, suggests we should not expect to occupy a privileged position in the universe, that any assumption of specialness will eventually be disproved. But this principle is not a law of physics. It is a heuristic, a useful guideline that has proven reliable in the past. One quirky response to cosmic insignificance is the overview effect, a cognitive shift reported by astronauts who view Earth from space. Seeing the planet as a tiny blue marble against the infinite void produces a profound reorientation of perspective, a visceral understanding of fragility and interconnection that words struggle to convey. The overview effect has been described as life-changing, spiritual, overwhelming in ways that transcend normal experience. Contemplating the Milky Way's size can trigger a similar internal recalibration, though without the direct sensory input of spaceflight. Truly absorbing the scale of the galaxy, its hundreds of billions of stars, its 100,000 light-year extent, its dark matter halo stretching into the void, produces something like vertigo. The mind reaches for familiar anchors and finds none. The numbers are too large, the distance is too vast, the timescales too extended for intuition to grasp. Some find this vertigo depressing. The universe seems indifferent to human existence, our entire civilization contained within a modest galaxy, orbiting a middling star in an unremarkable suburb. All of human history, every war and symphony and love affair, has unfolded on a pale blue dot circling a spark in a river of sparks. Carl Sagan famously meditated on this perspective, using the Voyager photograph of Earth from beyond Neptune to urge humility and compassion. If this is all we have, he suggested, perhaps we should take better care of it. Others find cosmic insignificance liberating rather than depressing. If the universe is not arranged for human benefit, then we are free to create our own meaning rather than searching for one imposed from above. The absence of cosmic purpose is not a void but an invitation, a blank canvas on which any significance we achieve is genuinely ours. This existentialist response to astronomical scale has appealed to philosophers and scientists alike. For you, drifting in this imagined space, the lesson is gentler. The Milky Way is smaller than we once thought, but it is still incomprehensibly vast by any human measure. 100,000 light-years contains more stars than any human could count, more worlds than any human could explore, more stories than any human could imagine in 1,000 lifetimes. Smallness is relative, and relative to human capacity, the galaxy remains infinite. Moreover, the act of measurement itself is remarkable. From a planet we have never left, using light we cannot touch, we have determined the structure and extent of our cosmic home. This is not merely astronomy, it is an expression of human curiosity at its most ambitious. We may be small, but we are aware of our smallness, which is more than most matter in the universe can claim. You drift toward a cluster of radio telescopes spread across a desert landscape, their dishes aimed at the sky in coordinated observation, like flowers tracking an invisible sun. This is one of humanity's listening posts in the search for extraterrestrial intelligence, and the question lingering in the night air is whether the Milky Way's size has any bearing on the likelihood of finding other minds somewhere among those hundreds of billions of stars. The short answer, reassuringly or disappointingly depending on your temperament, is probably not. A galaxy containing 100 billion stars or 400 billion stars is equally incomprehensible from the perspective of a species that has only confirmed life on one planet. Whether the Milky Way is the largest spiral or merely a medium one does not change the fundamental arithmetic of astrobiological hope or despair. What matters more than total size is the number of potentially habitable worlds within whatever size the galaxy happens to be. Estimates vary wildly depending on assumptions, but most astronomers agree that the Milky Way contains billions of planets orbiting in the habitable zones of their stars, those orbital distances where liquid water could theoretically exist on a planetary surface. Not all of these will be suitable for life as we know it. Some will lack atmospheres, others will orbit unstable stars prone to lethal flares, still others will be tidally locked with one face eternally baked and the other eternally frozen. But even if only a tiny fraction of habitable zone planets actually support conditions friendly to life, the numbers remain staggering. 1% of a billion is still 10 million. 1% of 10 million is still 100,000. The Milky Way's sheer stellar abundance means that even pessimistic assumptions about habitability leave room for enormous numbers of potentially living worlds. Historians still argue about the significance of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations suggested by these numbers and the complete lack of evidence for any. Physicist Enrico Fermi famously asked, "Where is everybody?" during a 1950 lunch conversation, and the question has haunted SETI researchers ever since. If the galaxy is old enough and large enough for intelligence to have arisen many times, why do we see no signs of it? Proposed solutions to the Fermi paradox span a remarkable range. Pessimists suggest that intelligent life destroys itself before becoming capable of interstellar communication or travel through nuclear war, environmental collapse, or technologies we cannot yet imagine. Optimists counter that we have not looked hard enough, that our instruments are too crude, that our search strategies are too narrow. Philosophers propose that we would not recognize alien communication even if we detected it, that truly advanced civilizations might have transcended the need for crude radio signals. One quirky aspect of the paradox involves galactic geography. The Milky Way is old, roughly 13 billion years, give or take. Even a civilization expanding at a tiny fraction of the speed of light could have colonized the entire galaxy multiple times over in that span. The absence of obvious colonization, no megastructures dimming stars on predictable schedules, no radio beacons sweeping the sky with mathematical precision, no probes arriving in our solar system to announce themselves, suggests either that such civilizations are extraordinarily rare or that they behave in ways we do not expect. Some researchers have proposed that civilizations might deliberately avoid contact with younger species, a scenario sometimes called the zoo hypothesis. Others suggest that the galaxy might be divided into territories or spheres of influence that prevent expansion into certain regions. Still others propose that we are simply among the first intelligent species to arise, that the cosmic conditions necessary for complex life have only recently become common enough to produce minds capable of asking these questions. For you, the relevance of galactic size to the question of extraterrestrial intelligence is tangential, but not negligible. A smaller galaxy does not mean fewer places to search. It still contains more stars than any search could cover in countless human lifetimes. The vastness is the point. Even a small galaxy by extragalactic standards is so large that absence of evidence is barely evidence of absence. We have scanned an infinitesimal fraction of the Milky Way's potential signal space, using instruments that might be entirely wrong for the task, looking for signatures that alien minds might not bother to produce. What the size discussion does emphasize is the galaxy's continued capacity to surprise. Just as astronomers revise the Milky Way's dimensions downward from earlier estimates, they may revise our understanding of habitable worlds, of biosignatures, of the conditions necessary for intelligence. The search continues not because we expect success on any particular timeline, but because the stakes are too high and the territory too vast to abandon. The detection of even microbial life elsewhere in the galaxy would transform human civilization's understanding of its place in the cosmos. The detection of intelligent life would be more transformative still, raising questions about communication, about values, about what it means to be human in a universe demonstrably shared with other minds. These possibilities justify the patient listening, the careful analysis, the decades of effort that have so far produced only silence. Your platform rises away from the radio telescopes now, their dishes shrinking to silver specks against the brown desert floor. Somewhere in that sky, perhaps, other minds are wondering about their own galaxy's size, revising their own estimates, searching for signals from neighbours they have never met. The silence might be temporary. The search is far from over. The journey softens now, your platform slowing its drift, the galaxy settling into a familiar glow beneath you. The stars pulse gently, their light ancient yet continuous, a lullaby written in photons that have travelled for thousands of years to reach this moment. You have come far tonight, through centuries of human understanding, through revolutions in thought and technology, through the gradual unveiling of a cosmos far stranger and larger than any ancient philosopher could have imagined. You have travelled through history, watching humanity stumble toward understanding with the persistence of creatures who refuse to accept mystery as an answer. From Babylonian ziggurats, where priests tracked wandering lights across the sky, to Galileo's modest telescope revealing the Milky Way as countless stars, from Henrietta Leavitt's patient measurements of pulsating variables, to Gaia's billion-star catalogue streaming data through the void, each step brought clarity, and each clarity brought humility. The Milky Way is not the universe. That idea died with Hubble's Cephids in Andromeda. It is not the largest galaxy. Andromeda claims that title in our local neighbourhood, and giants elsewhere dwarf them both. It is not centred on us. The Sun orbits 26,000 light-years from a supermassive black hole we cannot see. And its size, that number we sought with such determination across centuries, turns out to be smaller than generations of astronomers had assumed. 100,000 light-years across, give or take. Perhaps a bit less depending on where you draw the boundary, where you decide the fading stellar density finally drops below whatever threshold you have chosen. A disk of stars spinning around an invisible anchor, surrounded by a halo of ancient light, embedded in a sphere of dark matter, so vast and so invisible that it dwarfs everything we can actually see. This is your home, modest among giants, vast beyond comprehension. These are not contradictory descriptions, but complementary ones, perspectives that depend on where you stand. From within human experience, the Milky Way is effectively infinite, containing more than anyone could explore in any conceivable lifetime. From the vantage of the cosmos, it is a middling spiral in a middling group in a universe so large that the light from its far edges has not had time to reach us. Historians still argue about which discovery most profoundly changed our understanding of the Milky Way and our place within it. Was it Copernicus removing Earth from the centre, Shapley removing the Sun, Hubble revealing other galaxies, Rubin exposing dark matter? Each revelation built on the others, a cumulative demotion that left humanity perched on an ordinary planet, orbiting an ordinary star in an ordinary region of an ordinary galaxy, in what appears to be an ordinary corner of an extraordinary universe. One quirky comfort emerges from this pattern of ordinariness. If the Milky Way is typical, then whatever made us possible, the heavy elements forged in stellar cores, the stable environment maintained by a quiet yellow star, the billions of years of uninterrupted evolution on a planet with liquid water and a protective magnetic field, might be typical too. The conditions for life may be scattered across the galaxy, across all galaxies, waiting to be discovered or waiting to discover us. Our ordinariness might be the very thing that connects us to a universe teeming with possibilities. For now, you are drifting towards sleep, the stars dimming into softness around you. The Milky Way spreads beneath your imagined platform like a river of light, its current carrying you toward rest. You do not need to understand every detail of what you've heard tonight. You do not need to remember every name, every number, every twist in the long story of astronomical discovery. What matters is the feeling of scale that settles over you now, the recognition that you are part of something so much larger than yourself that language strains to describe it. The galaxy breathes slowly, if galaxies can be said to breathe, its rotation measured in hundreds of millions of years, its evolution stretching across timescales that reduce human civilization to an eye blink. Stars are being born somewhere in those spiral arms, nebulae collapsing under their own gravity, igniting nuclear fusion for the first time. Other stars are dying, shedding their outer layers into space, seeding the interstellar medium with the carbon and oxygen and iron that will someday form new worlds. The cycle continues whether anyone watches or not. You have watched tonight, at least in imagination. You have traced the long arc of human curiosity from ancient skygazers to modern spacecraft, from superstition to science, from a cosmos centered on Earth to a cosmos indifferent to our location. This arc bends toward understanding, though the destination remains hidden beyond the horizon. The Milky Way will continue long after tonight's journey ends. It will absorb its satellite companions, merge with Andromeda, transform into something unrecognizable over billions of years. Whether any intelligence will remain to witness these changes is unknown. Perhaps we're the first. Perhaps we're among many. Perhaps we're already being observed by minds we cannot detect. The silence of the cosmos is not an answer, but a question, and questions are what keep us looking upward. Sleep now, traveller. Let the stars wheel overhead in their ancient patterns. Let the spiral arms turn slowly beneath you. Let the dark matter hold everything together in its invisible embrace. The Milky Way is smaller than we thought, but it is still vast enough to dream in. That is enough. That has always been enough. The galaxy softens now, its light diffusing into a gentle haze around you. Your breathing slows, your thoughts drift. The numbers fade. 100,000 light years, 400 billion stars, 13 billion years, dissolving into something simpler, warmer, closer to sleep. You're still part of all this, even as you let go of the details. The carbon in your body was forged in ancient stars. The oxygen you breathe was released by dying giants. You're made of the galaxy, quite literally, assembled from material scattered by supernovae billions of years before your birth. The Milky Way stretches on without you, patient, unhurried, rotating once every 250 million years. It does not require your attention. It does not need your understanding. It simply is, as it has been since before Earth formed, as it will be long after any trace of humanity has faded. But tonight, for this brief moment, you have seen it. You have traced its history. You have measured its extent. You have contemplated its companions and its future. That is something. That is more than most matter ever achieves. Awareness, curiosity, wonder. The stars dim now to a soft glow. The spiral arms blur into ribbons of fading light. Somewhere very far away, Andromeda continues its slow approach, patient as gravity, inevitable as time. But that collision is billions of years away. Tonight, there is only rest, only the gentle turning of the galaxy beneath you, only the whisper of starlight across distances too vast to imagine. Sleep well, traveller, the cosmos will still be here when you wake,